Okay, a very important task and quite difficult task at the end for each wave propagation problem, that's the same case also for electromagnetic waves, is that we have to model somehow free radiation. And as we know, just looking here for this simple case of a plane wave in one dimension, if this is our boundary, but still in reality the waves would propagate out, we need a boundary condition or somehow a treatment at this boundary for these waves that they are absorbed and so that they are not reflected. However, we know putting a simple Neumann, homogeneous Neumann or homogeneous theoretical boundary condition would result in a full reflection and therefore make no sense. So a very efficient method which can't be made very accurately, which we will not discuss. We will discuss so-called absorbing boundary conditions of first order. And that can be extended to higher order and then almost be able to absorb any waves impinging at any angle at such boundaries is the following. Let's consider this case here, the one-dimensional case, where we know the exact analytical solution. So it is a plane wave in 1D. The amplitudes are constant. Clearly, they are varying with time, as shown here, but we should not have any decay of the waves. And then the analytic solution for the waves traveling in positive x direction is simply this p0 exponential function with argument j of omega t minus kx, where k is our wave number, just omega 2 pi f over the speed of sound. And when you take the real part, you get then the pure solution as we clearly have in reality. Here we have it with the complex ansatz. And the important point is if there is a traveling wave going in opposite direction, then it's almost the same. But as you can see here, instead of this minus here, you have a plus, and that models a wave traveling in negative x direction. So let's assume that we take here such a relation between time derivative and space derivative, and that is actually a decomposition of the second order wave equation. So perhaps I just sketch this. Okay, so as we know, our wave operator is 1 over c0 squared, second time derivative, minus the second space derivative. I just write it here with the Laplacian, operating on the acoustic pressure. And that, for example, is equal to 0. Let's say we excite the waves by any boundary conditions. And this wave operator can be rewritten and decomposed as 1 over c0 d dt plus the gradient, and I write here just d dx. Yeah, so we go here to 1d, then it's easier to do it. Multiplied by 1 over c0 d dt minus d dx. Yeah? And that is something, as we already learned in school, as you know, it is something like a plus b multiplied by a minus b. And that is a squared minus b squared. Yeah? And so you see the mixing terms, as you look here, will cancel out, and exactly what we get back is 1 over c0 squared. The square of this, which is second order time derivative, minus the second order space derivative. So this is this decomposition of a wave operator you can do. And you see that we can decompose it once in an operator where we have a plus and once in an operator where we have a minus. Now let's go back to our problem at hand. And we take here the first term of our decomposition and say, okay, this term should be 0. And also concerning the units, it's okay because we have here the scaling c. It could be also here 1 over c, but you can also take the c here since we put it equal to 0 and we assume that the speed of sound is constant. And what you see is actually that you can here express the space derivative by the time derivative and scaled with 1 minus 1 over the speed of sound. Now let's have a look if this is fulfilled by the wave traveling in positive x direction, because our goal is that waves traveling in positive x direction when they come up to the limiting boundary of our computational domain that they can pass. On the other hand, waves coming from outwards, that they will be reflected. So they are not allowed to go into the computational domain. That would be then an optimal absorbing boundary condition because the waves being generated inside the domain can travel out and nothing can travel back. Okay, since we have the analytic solution, it's easier for us to compute the time derivative and the space derivative. Well, the time derivative now for a wave propagating in positive x direction is just a scaling with j omega. And the space derivative, as we see, is a scaling with minus jk, the wave number. And we know that the wave number, I just write it again here, is just omega over c, the speed of sound. So you see that this part, since it is scaled by c, is nothing else as minus j omega. And so you see this really cancels out and becomes exactly 0. So it is even optimal in this case. Now let's see if waves coming from outside, what happens with them. And this, as we know, has now this solution. Instead of the minus, we have here the plus. So the time derivative is again this part here. Now the space derivative is plus j omega, which gives us plus here jk, sorry, the derivative. And with c, it gives us j omega. And so you see this is not equal to 0, and we will have really full reflection, which means these waves can pass, and the waves which would come from outside would be reflected. So this is even in this sense, although it is as simple, this decomposed part of the wave operator, it is optimal. However, this is for 1D, and in general, the absorbing boundary condition now in 3D, we know we not only have a derivative of the pressure with respect to one space coordinates, is the derivative with respect to the normal vector. So, and therefore, this is an approximation which becomes exact if the waves impinge orthogonal to the boundary. In all other cases, we will have partial reflections. Anyway, impinging orthogonal gives us an optimal boundary condition. And as you see, it is quite as simple, since in the weak formulation, we do the integration of parts by the Laplacian operator multiplied by the test function, which is our p prime. And this integration by parts gives us this boundary integral. And now this spatial derivative is simply substituted by the time derivative, which means in addition to our standard stiffness and mass matrix, we get here a damping matrix, and which is computed quite simple, yeah, as you look here. So we do the ansatz for the test function and for the unknown P acoustic itself. So it is a kind of a mass matrix because the base finite element basis function are just multiplied with each other. We have the scaling with 1 over c, and this has just to be evaluated at the boundary where we need free radiation. Okay, let's have a look to a very simple setup, but nicely shows the effects what we really have. You can see here the computational domain already. Here in the center of this square domain, we have a point source, and you see radiating waves outside. And clearly, the main problems what we get here for a homogeneous Neumann boundary condition is when they impinge here, 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 and here. The boundaries, then they get reflected, and you get here a total overlap of reflected and outgoing waves. On the other hand, when we apply here on this boundary such a simple absorbing boundary condition of first order, you see that they get here very nice absorbed, but in the corners clearly, where the waves do not impinge orthogonal, we get here some deformations of the outgoing wave, so we will have partial reflections. Do you have an idea for the simple setup how we should change the geometry here so that we get no reflections? How should we shape the limiting boundary of the computational domain? We have an idea. So we have this information that when waves impinge orthogonal, yeah, so you see in this sense, for example, here this is a wavefront and this impinges orthogonal to this boundary, but in the corners clearly it's not orthogonal. So which shape the boundary should have so that with this simple absorbing boundary condition of first order we get optimal absorption and no partial reflections at the boundary. You can also write something in the chat. Exactly. Thank you very much for this comment in the chat. Exactly, it should be a round shaped. So actually this boundary should not be a square, it should be a circle, and it would work optimal. That means also for us in general setups, when you have such a simple absorbing boundary condition of first order, then perhaps you make a sphere, a limiting sphere. Sometimes it's not possible or just possible with a lot of additional finite elements. So let's look what happens in our case here in 2D. In 3D, it's quite similar. Well, we are looking here at two observation points, P2 and P1. We excite here with a Dirichlet boundary condition having just one sine pulse as shown here. And if you look here now at P1 and P2, well, you see that this is looking quite nice. Here we have some deformation, but as it should be, more or less, the energy is really taken out by this absorbing boundary condition. But we have clearly also for the second point here, which is P2, So this is this point, and this is P1 in the corner. We have this one. Clearly, the amplitudes are smaller because here you have already a longer distance the waves run, and you know we have a decay by 1 over distance. Okay, so it is clearly not optimal in this sense, but it is somehow working, and in practice, a boundary condition for modeling free radiation heavily used, let's say. A better boundary condition perhaps is a so-called PML. I just show it to you here. So a PML, I just write it here. PML means perfectly matched layer. So I just show it here in this sense. So let's say this is the computational. What's going on here? I want to have this one. So this is our computational domain. And then in addition, you have here a further computational domain which surrounds your propagation domain. So this is the PML domain, and this is here the propagation domain. And we are really able in this sense that this is a so-called damping layer, which a property that at the interface, which is here between propagation and damping region, we have perfectly matching. So we have no reflection. We efficiently damp the amplitude of the wave. And when it impinges here, it should have already a very, very low amplitude. Here it will be reflected, will be again damped, and then clearly it will re-enter the propagation domain. But if you design it correctly, then the reflected parts here will be so small that you can neglect it and will be within machine precision. Okay, so this is something which we will discuss in detail because it's quite sophisticated how you design it and how you can prove it that it is, for example, perfectly matched, that we will discuss in multiphysical simulation too. Okay, so in this sense, we come now to our final chapter, which is the coupling between the acoustic field and the mechanical field. And in this sense, we will discuss both the coupling via a modeling of the acoustic waves by the acoustic pressure or by the scalar acoustic potential. So here are two typically examples. This is an ultrasound array in this sense that you have here this in yellow. What you see are piezoelectric transducers. It is a two-dimensional array where you can have delayed excitations for all the different piezoelectric actuators there, and therefore you can get such a focusing of the ultrasound wave. And if you have an obstacle here, you get reflections, and you switch from the actuator mode to the sensor mode, and you can then pick up the waves again by the piezoelectric effect and can make pictures of it in this sense. For example, in medical science, for example, to get pictures within your body for some investigations, or also clearly for non-destructive testing. Here, since the fluid is in more or less water, we should have a strong coupling. So the coupling from the vibrating structure to the acoustic field, and from the acoustic field back to the mechanical vibrating transducers should be taken into account. On the other hand, There are also a lot of applications where we just need a so-called weak coupling. Here a transformer where due to Lorentz forces on the windings, we get vibrations within the tank, which is filled by oil. So you have then a transfer from this vibration over the oil to the tank. This is outside the tank, and the tank radiates then due to the vibration, radiates acoustic waves. And here a weak coupling is more or less enough in this sense. So that means you can do first a computational of the vibrating tank, take and pick up the vibrations on the surface and do then a pure acoustic simulation to get the radiated field. So this we call here a weak coupling, and this a strong coupling. And both clearly we will discuss here in this sense, especially we will discuss the strong coupling, and it is then up to you when you have any problem at hand to decide if you need a strong coupling and need to solve simultaneously for acoustic and mechanical field, or you can do a sequential computation, first compute the mechanical field and then just the acoustic field. Okay, so what is clear, we have two partial differential equations. The partial differential equation for the mechanical field and for the acoustic field, both we already have discussed. And it is a so-called surface or interface coupling as shown here, because on this domain, we just have to solve the mechanical partial differential equation to get the vibration of this body. And then we have the interface to the ambient fluid where waves are generated. And in this domain, we have to solve for the acoustic field. And at the interface, we have to fulfill the so-called coupling or interface conditions as they are called. Importantly is the following now for our derivation, that we fix the direction of the normal vector. You know, any surface is characterized by the normal vector. In most cases and books, you will find that the normal vector n is accordingly to the normal vector of the structure, as we see here. We know that the normal vector always points out of the volume, which would mean that the normal vector here for the acoustic domain would point into the structure. Okay, so we take now the normal vector of the structure, which means we get a minus for the normal vector for the acoustic domain. Okay, so what do we have to fulfill? We have to fulfill the so-called kinematic boundary or interface condition and the dynamic one. The kinematic one is according to the velocities and the acceleration. So when you look here at this part, then we know the following, that the vibrating velocity at the surface, therefore we have the dot product with the normal vector, can be expressed by the mechanical displacement, the time derivative of the mechanical displacement, and that has to meet the particle velocity in normal direction. And we know the particle velocity can also be simply described by minus the gradient of the acoustic scalar potential. So you see, we have in this sense a direct relation between the acoustic scalar potential and the mechanical displacement. On the other hand, this also has to be fulfilled clearly for the time derivatives. If you take this equation here and take a time derivative, then we get, instead of the surface velocity, the surface acceleration in normal direction that has to meet the time derivative of the particle velocity in normal direction. The second coupling, so this is a coupling, we can say, which couples the mechanical vibration into the acoustic domain, into the acoustic particle velocity. And on the other hand, if we have any pressure forces, and these are the acoustic pressure forces, so perhaps it makes sense to write here AA to directly know it's the acoustic pressure, acts as a pressure force on the mechanical structure. So the stress tensor in normal direction giving you the stresses on the surface has to be balanced by the acoustic pressure force. The minus clearly we get, as you know, pressure is always acting into a body, and therefore we get here this minus. Yeah, we have here nice relation, what is always missing here, but we have it actually also on the other slides, is the sense that the acoustic particle velocity, the time derivative scaled with the density, is equal to minus the gradient of the acoustic pressure. As you know, this is the linearized conservation equation of momentum. And since we can put in here for the acoustic particle velocity, since it is rotational free, we can express it by the minus gradient of the acoustic scalar potential. We get here this nice relation also between the acoustic scalar potential and the acoustic pressure that we will need in order then to express our two interface condition, the kinematic and the dynamic ones for the acoustic scalar potential when we model the acoustic waves by the acoustic scalar potential, and ones for the acoustic pressure when we model the wave equation by the acoustic pressure. Okay, so looking here, we have exactly this relation. We are looking now for the acoustic potential formulation. In this sense, we know that we can express here the acoustic scalar potential time derivative scaled with the mean density is equal to the acoustic pressure. And we have this direct relation between the acoustic particle velocity and the scalar acoustic potential. So our continuity of velocities can be simply expressed, as you can see here, by our primary quantities, the mechanical displacement, actually it's, as we see, the time derivative, and it has to be equal to the normal derivative of the scalar acoustic potential scaled by -1. Okay, that means our coupling conditions according to the continuity of the velocities is here. And so we see how the mechanical displacement couples to the acoustic PDE, which we will see soon. And on the other hand, we know that the stress tensor on the surface has to be balanced by the acoustic pressure. And here we clearly use this relation. Should go this here, and we see that we can here substitute then the surface stress vector by this term here, and this shows how the scalar acoustic potential couples to the mechanical PD. Okay, and that are both at the surface being the interface between the solid and the fluid. On the other hand, when we have acoustic pressure formulation, well, we have here the following. We know according to this equation here, which is the linear momentum equation, the relation between the acoustic particle velocity and the acoustic pressure. When we project this on the surface, meaning we do a dot product of this equation with the normal vector, we get here the normal derivative of the acoustic pressure, and we see that has to be equal to minus mean density time derivative of the acoustic particle velocity dot product with the normal vector. And we know that we have the continuity of the velocities. So this is equal here to the mechanical velocity, which we just have denoted by v, which is the time derivative of the mechanical displacement. So we see that now this normal derivative is here can be expressed by the mechanical acceleration, since we have here the second time derivative of the mechanical displacement. So we see by this coupling term how the mechanical displacement couples to the acoustic PDE, and this we already had as a natural condition for the acoustic pressure and the surface stress of the solid, how the acoustic pressure couples into the mechanical PDE. Okay, so we have now both coupling terms, the dynamic and the kinetic one, for the acoustic pressure formulation, and as shown here for the scalar acoustic potential formulation. Okay, so that means we can now derive the weak form of our coupled system. For this, to go over from the strong form to the weak form, we introduce our test function. We call them U prime for the mechanical PDE and P prime for the acoustic PDE. Multiply this partial differential equation, the mechanical one and acoustic one, by this test function and integrate over the computational domain. So we get here our weak form of the mechanical PDE, where we already have done an integration by parts, and this surface term now, which we quite often have neglected because at the surface we have zero stresses, but now we have this surface term where exactly this term here can be expressed by the acoustic pressure or scalar acoustic potential. And on the other hand, in the weak form of the acoustic PDE, due to the integration by parts of the Laplace operator, we get this surface integral where we have the normal in here, the normal derivative of the acoustic pressure. Yeah, and you see, I take here NA subscript A, meaning that is the normal vector for the acoustic domain, and we know that this has to be multiplied with -1 when we would take, so we can also write here, this would be minus dB acoustic dN solid. Yeah, as also shown here, normal vector of the solid, normal vector of the acoustic domain. But we know they have this simple relation via -1. Okay, now we can substitute here in these two green terms our physical interface conditions, and that is as shown here. So to make it, because we have here just neglected the subscript A, but I just put it again here so that we know this is here the acoustic pressure. I also put it here and here. Yeah, and so we see how the acoustic pressure enters into the weak formulation of our mechanical partial differential equation at this common interface, which we have called gamma A for acoustic, S for solid, and how the mechanical acceleration, since we have here the second time derivative of the mechanical displacement, enters the weak form of the acoustic PD. Okay, on the other hand, since we have this relation here, so that we can express the time derivative of the mechanical displacement in normal direction by the scalar acoustic potential, which we perhaps here also rewrite in this sense here by d psi dn. And we also can express the acoustic pressure by the acoustic scalar potential. So this, which is the dynamic interface condition, and here the kinematic interface condition. And so we see here now, when we describe the acoustic field by the scalar acoustic potential, we see that we get here this part, how the scalar acoustic potential enters the weak form of the mechanical PDE and how the mechanical displacement enters the weak form of the acoustic PDE. Please also look at this part here, that we have here a time derivative and we have here a time derivative. And we have here a vector, which is the test function, and here a scalar, and we have here a scalar and here a vector. So when you use the same basis functions for the mechanical displacement and for the scalar acoustic potential, as well as for the test functions, then we get here coupling matrices when we substitute there these basis functions, which are transposed to each other. We just have to multiply this weak form by -1, that we also get the plus on this side here. So that's nice that at the end we get here, due to this coupling, a symmetric, at the end, a symmetric system matrix when we do space and time discretization. However, if we look at the acoustic pressure formulation, this is not possible, yeah, because here the acoustic pressure directly enters, and here the second time derivative of the mechanical displacement enters. So this is the big difference we have here. So as you know, that some algebraic solvers can be quite efficient if we have a symmetric system matrix, which is never the case here when we use a coupling with the acoustic pressure, but can be when we describe the acoustic field by the acoustic scalar potential. Okay, that is also shown here now in a semi-discrete Galerkin formulation for the pressure formulation. As you can see here, the coupling matrix here, how the pressure couples into the mechanical semi-discrete Galerkin formulation, because we are still continuous in time. This is the second time derivative, and XU collects all the mechanical unknowns, the displacements in x, y, and z direction at all the nodes of the computational domain for mechanics. And xb is here with this double dot, the second time derivative of the acoustic pressure unknowns at all the nodes of our acoustic domain. And you see that this is clearly not a symmetric stiffness matrix, that is not a symmetric overall mass matrix. Here we see how the mechanical displacement, actually acceleration, clearly enters then the semi-discrete formulation of the acoustic system. So inherently we can say we get here an unsymmetric system. We will do also clearly, or have to do, a time discretization. We use just Newmark method, as we discussed, for mechanical system and acoustic system, and we will get out then the algebraic system of equation with a system matrix which is unsymmetric. On the other hand, as shown here, we get here for the acoustic potential formulation the coupling within this part here. Yeah, so you see you have no coupling within the overall mass matrix, within the overall stiffness matrix, but the couplings come in, as we call here C, the stiffness, the damping matrix. This is due to the coupling conditions we get, and this is our final system. And as I have told you, it is possible to make this symmetric. So the system matrix then at the end, when we do also time discretization, is a symmetric one. Please also note that from the physical point of view, it is not a damping matrix. In this case, although we call C a damping matrix because it is multiplied by the first order derivatives of the mechanical displacement and the scalar acoustic potential. Okay, from the physical point, it cannot be a damping matrix because we have no diagonal entries. Yeah, the diagonals, as you can see here, are zeros. That is coming to our coupling condition. Yeah, so also for the coupled system, then of our ordinary differential equation after space discretization, well, we can go to the frequency domain and do a harmonic analysis of the coupled system, or we do also a Newmark time stepping scheme and do transient analysis for each time step of interest, or we can also do an eigenvalue analysis of the coupled system, which is clearly of interest when a full coupling is necessary. So we will see how the eigenmodes of the mechanical structures are changed due to the coupling, because we also have this back coupling from the acoustic field via the acoustic pressure to the mechanical vibrating structure. Okay, so you see, this is a straightforward approach at the point when we know what are the coupling conditions. We then can incorporate the coupling conditions, and that is also always the case. Please be careful. You always do it on the continuous level, so meaning within the weak formulation, before you then do any approximation in space and time. Yeah, very often it would be of great advantage if we can do a so-called non-conforming grid technique. Yeah? Non-conforming grid technique means in this sense that you can have, or you generate your computational mesh for the fluid, the ambient air, for example, and for the structure individually. You then need also the surface elements here, and you have a method which glues together these non-conforming two grids, here coming from the fluid, the ambient air, and here from the structure. And that makes life easier, especially if, for example, you need a finer mesh within the structure as for the ambient air, where you solve for the acoustic partial differential equation. A typical example what we have here is the loudspeaker. You know, we have frequencies which is somehow between 20 hertz, and perhaps you go up to 20 kilohertz. Above 20 kilohertz, we cannot hear the generated sound. And we know that the wavelength is the speed of sound over the frequency, which is about 343 meters per second over the frequency. On the other hand, what you see here is the membrane of a loudspeaker, and the membrane of the loudspeaker here, the thickness D will be about 1 millimeter. Yeah? So it is quite thin compared to the wavelengths. When you look here up, for example, at 1 kilohertz, then the wavelengths would be 0.343 meters. So a quite big difference to the geometric dimensions you have in the structure. This is also a special topic where we have done a lot of research and where we provide the teaching of these techniques in multiphysical simulation too. Okay, are there any questions so far? of this coupling procedure we have between the mechanical system and the acoustic system. Okay, so this is more or less was our final part, and as a motivation, we have also multiphysical 2 where we go towards coupled field problems with nonlinearities like computational electromagnetics and mechanics or computational electromagnetics and the thermal field, and where we also discuss about wave propagations, have special topics like this perfectly matched layer method, and also special topics towards non-conforming grids and those things. Okay, so I look at the chat, there is no question up there. Then I think we can go over to the homework you have done and discuss the homework. So in this sense, you have submitted you have submitted 2 homeworks. So the first one was towards heat conduction and coupling to mechanics, and the second one was piezoelectricity. And in this sense, we should start with the first part, which is heat conduction and coupling to mechanics, where you had to solve 8 tasks. I also have a list and put in the points you get for the presentation. So currently, no, sorry, 8 persons have presented, and not all are currently online. Anyway,